So today we're looking at extreme value theorem. And so let me start off by actually writing out the theorem for us. So if f of x is continuous and closed on a to b, so some interval, then f of x is guaranteed a maximum and minimum value on the interval being a to b. And that is an and, you get both. We talked about in class critical values, and the formal definition would be if f of x is continuous on a domain, then all points in the interior of the domain where f prime of x is equal to 0, so the derivative is equal to 0, or f prime of x is equal to undefined, are critical values. This interior of the domain piece tells us that endpoints are not critical values, no matter what's happening at the endpoints, even if the derivative is 0 or undefined. All right, so given that, let's talk a little bit about the steps that you take to find your extreme values. So how to find them. First thing you want to look at is your domain, because you may have some issues, or that can do something like give you a closed interval, which might help you figure out that EVT holds. So we always find our domain. Remember, the three domain issues we look at are where you have a fraction, if you have an even root, or if you have an ln or log. Those are our major domain issues. Second thing we do is find f prime of x and set that equal to 0. And we also find f prime of x equal to undefined. We go through and set up a sign chart within the domain. The sign chart includes all of the points where f prime of x equals 0 and f prime of x equals undefined. And then 4, we look at the y values of possible max and mins based off of our sign chart. And then 5, we figure out what they are, and we figure out if they're local or absolute. Things that we might want to remember: what does the sign chart look like for a max? That would be where you have an undefined or 0 slope, so this is for f prime, and your maxes always will change from positive to negative. Your minimums, though, will change, same thing, undefined or 0 slope, from negative to positive. We can also talk about endpoints, and we'll do that if we end up coming across some endpoints. So I'm going to start off with a polynomial example. So in this problem, we know that we have an undefined, a defined domain of all real numbers, which means that EVT will not hold because we don't have a closed domain. But let's go through step 2, which says take the derivative, which is 4x cubed minus 24x squared plus 36x. Set it equal to 0. And set y prime equal to undefined, but we know that for polynomials, our derivative will not be undefined. Our next step is to try to figure out how to solve this guy, and I'm going to factor out the greatest common factor, which leaves me x cubed minus 6x plus 9 on the inside, which then is also still factorable. It's x minus 3 equals 0. So we get, take each factor equal to 0, and these are the same exact factor. It's actually called an even root, and solve each of these equal to 0. Oh, not an even root, I'm sorry. Oh yeah, it is an even root. Okay, so now we want to make our sign chart here. We're making our sign chart off of f primed of x. On my sign chart I'm putting in 0, and on my sign chart I'm putting in 3. Things that are helpful to know is if you are dealing with an even root, we don't even need to look at it when doing our sign chart. So what that means for us is I'm going to do my sign chart, and I'm only going to care about the values in 4x. So negative 1 substitute into 4x will give me a negative. Positive 1 substitute into 4x would give me a positive. And something like 1,000 would make this positive. The other way to think of it is 4x is a line that goes like this, increasing, where your 0 happens at the origin. So that's why I have negative, positive, and it's still positive after. So at 3, I'll write down that that's the even root. That's why the sign doesn't change. So when we look at this, the only time we have an extrema would be here, and our sign went from negative to positive. That is, so let's draw out a little picture here. We're decreasing, we're flattening, we're increasing, we're flattening, and then we're still increasing. So just by looking at this, I know that this is a minimum, but based off the fact that it's a polynomial and the arrows, that's actually going to be an absolute. And I meant to write an A, not an L. An absolute. Because we never go and decrease again. So we decrease to the minimum, but we don't ever go back to decreasing. So I'll never have a chance for the function to go below that minimum point. What I will show you is the actual graph, which I think I have saved. Paste. Yeah, there it is. So here's the actual graph of the function. And you can see that this was, if this wants to listen to me. So this here was our minimum, and it was absolute. And what happened at x equal to 3 is it flattened and then kept increasing. So you can tell that the negative in my sign chart tells me that the function decreases. The positive tells me that my function increases, and that the positive again tells me that my function increases. This is the graph of the function and not the derivative. So in this one, we found one absolute minimum, and that was it. So the absolute min occurs at f of 0 equals 1, and I substituted that back into here because f primed of 0 is 0, and f primed of x changes from negative to positive. All right, so in part 2, I'll do another problem for you.